Hello guys, it's Richard once again, and today we are continuing and probably we will finish compounds and stoichiometry. Compounds, UNDS, and stoichiometry. So, last time that we discussed compound and stoichiometry, when we started it, we went through molecules, we did moles, we did molecular weight, we did equivalent weight, and then we did equivalence, and then we finished with normality. Let me touch a little bit on normality before we move on to the next concept of this chapter. And also, I'm using a tracker, so it follows me everywhere I go. Pardon with me if you can see the board, it follows me, not the board. So when we talk about normality, it is a measure of concentration. It is just a measure of concentration, but in equivalence per liter. So normality is a measure of concentration, right, of a substance. The substance is what we are looking for, maybe a hydrogen ions, hydrozonium ions, protons. So a measure of a concentration of a substance in equivalence per liters, right? So if you have any compound and you basically or mostly acidic and then alkaline compounds and you want to find the normality of it, you just divide the equivalence by the liters of it. Now there is a formula for normality that we can use to calculate it, pretty much simple. So the formula for normality, right, it will give you the molarity of the compound itself, of the entire compound, right, of the compound itself, divided by n, where n is the number of equivalents or the number of particles that we are looking for, right? So by so doing, if we say we have a compound, let's say we have one normality of H2SO4, right? One normality H2SO4, right? What we mean is that in this H2SO4 we have 1 mole per dm cube or per liter of H plus ions, right, in this compound right here. So the normality is the concentration of the thing that we are looking for in the compound, not the entire compound. Now the concentration of the compound itself might change, but then we can also use the normality to determine the concentration of the entire compound by using this equation, right? So if we said that one normality would give you, of H2SO4 has 1 mole of hydrogen plus in it, what is the concentration of H2SO4? So therefore, we're going to have 1 equals to the concentration of H2SO4, right, divided by the number of equivalents. And as we told you, the equivalence is basically the power that if H2SO4 dissociates completely, the amount of hydrogen ions or the amount of substance that we're interested in that it will produce. In this one specifically, it will produce 2 equivalents of H2SO4 because there are 2 hydrogen in this H2SO4, which is the sulfuric acid. So therefore, the molarity, which is the concentration of the solution, is going to be of H2SO4 is going to be just 2 by 1, which would give you 2 mole per decimeter cube or liter. Let's use liter to make it simple. So that is normality for you. If you have any question, slide into my DMs. I don't have a lot of followers as of now to not be looking at DMs. Can afford that. So after this, we are going to go to representation of compounds, right? Representation of compounds. I'm going to also wipe this off the board, clean this off the board entirely, and then move on with it. So when we talk about representation of compound, we are just talking about how a compound could be represented in our day-to-day encounter with them, whether it's being in our textbooks or in real life. Now, we already talked about two ways in which we can represent compounds, and one is the Lewis dot structure, right? So the Lewis dot structure is using the number of valence electrons to, represent a compound. The second one, which is 2, is we could also talk about molecular geometries, right? Molecular geometries. So molecular or electron geometries are also a way that we could represent compounds. Now, on our day-to-day activities, like in classes like organic chemistry, you would see arrangements such as this. If you see like this arrangement of CH4, it is just the skeletal arrangement of it. So you're also going to see a skeletal arrangement, right? The skeletal arrangement or the skeletal representation of the compound. So another way that we could represent them is writing their molecular or the empirical or the molecular formula. So another way for is the empirical formula, and then the fifth way is the molecular formula, right? The molecular formula. Now the empirical formula is the lowest whole number ratio, right, between the atoms that make up the compound, And then usually ionic compounds are always written in their empirical formula because ionic compounds don't form molecules once again. But for the molecular formula, it is the exact ratio, right? It is the exact ratio in which the atoms combine. So the exact ratio in which the atoms will combine, right? So for instance, if we take this compound, for instance, C6H12O6, this right here is a molecular formula, right? Or it's a molecular representation. And what it tells us that no matter where you go in the universe and you take this compound is sugar. Most of us know this already. No matter where you go in the universe and you take a sample of sugar, right? 1 mole of each sugar molecule is going to contain 6 atoms of carbon, and then it's also going to contain 12 atoms of hydrogen and then 6 atoms of oxygen. It doesn't matter where you go. That is the exact ratio that the sugar compounds do what? Arrange themselves in. Now, in this same sugar, we could also go 6H2O, right? When we find this is also a representation of sugar, but it's empirical, because it's a whole number ratio. So if we divide through here by the lowest common denominator, 666, it's gonna just cancel 1 and then 2 here, and we're gonna have 6H2O. This is the empirical formula right here. It is the lowest whole number ratio that we could distinguish between, that we could find between the compounds and the atoms that forms up the compounds. Now, from here, we are going to move into the law of constant composition, right? They're still under the representation of compounds, but the law of constant composition. Now, the law of constant composition, is basically related to the law of conservation of energy, law of conservation of matter. The law of constant composition states that any pure or a given compound, right, gives the simplest whole number ratio of elements in the compound. So any the law of constant composition states that any pure substance, right, give a compound will contain the same elements in identical mass ratio. The law of constant composition states that any pure substance that you take, a compound in this case, will contain the same whole number ratio of the atoms that makes them up, right? So any pure substance, into bracket a compound, right? Into bracket a compound will contain the same whole number ratio, right, of the elements that makes them up, right, of the atoms or elements that make them up. So, as for instance, the example that I did make here, let's take water for instance. If we take H2O, which is our water, it doesn't matter where you go in the universe, the water will always contain 2 atoms of hydrogen and 1 atom of oxygen. But maybe its physical properties might change, like density could change, because density depends on extrinsic factors, right? And depending on where you are, the outside factors might vary. But the compound water will still contains the same amount of the same whole number ratio of oxygen and then hydrogen. Now, once that we have the law of constant composition put down, let's move on to the percentage composition. So that is constant, the law of constant composition. We are moving on to percentage composition. So when we talk about percentage composition, it's basically how much of a specific atom is in the entire compound, right, in percentage wise. So if we take an entire atom to be 100%, an entire molecule or a compound to be 100%, how much of that 100% is of a specific element or atom that is inside that molecule or a compound, right? So in so doing, if we want to find the percentage composition, the percentage composition, right, of any element, let's say the percentage composition of element X in any compound, right, it is going to be the mass, right, the mass or the molar mass. In this case, let's use the molar mass. The molar mass of element X, right? First of all, let me make an inference. If we have a compound AX, let's say this is our compound. The entire compound is AX. If we want to find the composition of X in a compound, it is the molar mass, which is element X, divided by the entire molar mass of the compound. So the molar mass of the entire compound, which is AX, multiplied by 100, because 100 gives us the percentage. Percentage per 100. Cent equals 100. Percent divided by 100, right? So that is the percentage composition that we do have. So let's really move forward and then calculate, like just do one calculation. So what is the percentage composition of chromium in this compound? K2Cr2O7. Cr2O7. Okay, so we said that the percent composition is the molar mass of the substance that we are looking for divided by the molar mass of the entire compound multiplied by 100. So what we are looking for over here is chromium. So the molar mass of chromium, which is mm of chromium, would give us in this compound, chromium, the atomic mass of chromium is, or the atomic weight of chromium is 52. You're gonna get 2 times 52, which is 2 times 52 grams per mole, and 2 times 52 will give us 104 grams per mole. Let's do it for the entire compound. So the molar mass of K2Cr2O7 would give us 2 times potassium is like 39 grams per mole. Put the units there, grams per mole, plus chromium, which is 2 times 52 over here, 52 grams per mole, times the oxygen, which is 7 times 16 for oxygen. So once we do have this figure out, we could say that 2 times 39, even if it was 40, and on the MCAT, please, the MCAT doesn't test your ability to really like plug in and chug. It tests how good you can relate units. So I'm gonna assume this is 40, right? So 2 by 40 is 80, right? So I'm gonna, and even if it's 39, it will be 80 divided minus 2, which over here will be 78. So plus, over here already find it as 104, plus 7 by 16, right? Even if I took it to be 15, right? Even so that the calculation will be simple, 7, 5, 35. So 5, remember 3, which is 717 plus 1, which is going to be 105. But since I took it as 16, I need to add 14 more to it, because I took 1 off, or I need to add 7 more to it because I took 1 off, and then 1 by the 7 will give us 7. So if I add 7 to this would be like what, 12. So 2, 1, 1, 1, 2. Right here, 1, 1, 2 is what this would be. And if we add all of these together, 104, 112, 78, we are going to get, for this is 8 by 2, you're gonna get 10. 10 plus 4 is 14. Remember 1, and this is 9 over here, and this is 2. So we're gonna get 294 for the entire molar mass, which is 294 grams per mole. Now I don't mind if you have approximate, I have assumed, but so it's going to differ a little bit. So by so doing, if I want to find the percentage composition of chromium over here, is going to be the 104 divided by 294 multiplying by 100. Now, if you can do 104 by 294 in your head or on the paper on the MCAT, be my guest, right? But if you cannot, just assume, let's assume that this down here is 300, because we have like 6 to make it 300. And then up here is 100, right? So in that case, we are going to get 1 over 3, right? Which is 0.333, which is like 33%. So an equivalence of 33%. So the chromium composition in it will be around 33%, but since I approximated these numbers on the MCAT, I'm probably not going to find 33%, as the answer, but I'm gonna find something like 35. It's close enough. So that is how you move fast when you are solving like calculations in the MCAT questions. Approximate to the nearest whole number and do the math. So that is the percentage composition. And when we were discussing about the empirical and then the molecular formula, that we said the empirical was the lowest whole number ratio, and then the molecular was the exact weight. We did not find how to calculate for the empirical and the molecular formula of a compound. So let's use this for instance. What are the empirical and the molecular formula for a compound that has 40.9% of carbon? So carbon in this compound, C equals to 40.9% of carbon, comma, also has 4.58% of hydrogen. So the hydrogen over here is equals to 4.58%, and then oxygen will give us 54.2%. 54.2%. Now, once you get a question like this, assume that you have just, and then the question goes on and say that and has a molar mass of 264 grams per mole. So a molar mass of the whole compound has a molar mass of 264 grams per mole. So when you have this, assume that the entire mass of the compound is 100 grams. You can assume that the entire mass of the compound is 100 grams. So if the entire mass of the compound is equal to 100 grams, then this 40.9 would be the grams of carbon in the compound, right? So for the carbon, we have the 40.9 grams. 40.9 grams. For the hydrogen, we have 4.58 grams. And for the oxygen, we do have 54.2 grams. And if these are the grams in the compound that we do have, let's divide through by each individual's molar weight or molecular or atomic weight, because they are atoms. So let's divide by the atomic weight. So the carbon will be 12 grams per mole. Hydrogen will be 1 gram per mole. Oxygen will be 16 grams per mole. Now if you do it, the gram would cancel gram. You're gonna have 40.9 divided by 12. Let's assume that it is 41 divided by 12, right? So if 12 by 2 will give us 24, so 12 times 4 will give us 8, 48, right? So let's say 12 by 3, 12 by 3, 12 times 3, 236, 31, 3, right? Yeah. So let's say 12 by 3, 12 goes here, 1 goes here, 3. We get 3 point something. Let's say we're gonna get 3.4 moles, right? And then over here, we get 4.58 mole. And here 16 divided by 54, we are going to also get another 3.4 mole. Over here like this. So once we do get here, we divide through by the lowest mole, right? So if we divide here by 3.4 mole, divide here by 3.4 mole, divide here by 3.4 mole. So this would be just like 1 mole left. Over here is going to be 1.3. It's going to be 1.33 mole. And this would also be 1 mole left. So if you are told to write the empirical formula for such a compound, you are going to get C, which is 1, H, which is 1.33, and then O, which is also 1. But 1.33 is not something that you can just, let it hang around like that. So we can multiply through the entire 10 by 3 to make this a whole number. So if you multiply through by 3, we're going to get C3 H4O3. Right? So you're going to get this. So this over here will be the empirical formula. EF will be the empirical formula. Now let me run through why we did each individual step like that. So first of all, you get the compound and then the composition of the compound. Carbon was 40.9%, hydrogen was 4.58%, and then oxygen was 54.2%. Right. Once you get it in this form, what you do, and then the molar mass is given, what you do is assume that the entire compound is 100 grams. If you assume that the entire compound is 100 grams, then all these percentages directly converts into mass. The reason why they do convert into mass is that I said the mass of the compound is 100, and then you said in the compound there were 40.9%. So which means 40.9 grams is carbon, right? It directly converts. So one, we directly converted them. So over here, one is direct conversion to grams, right? Direct grams conversion. Now, once we have converted them into grams, we need to also convert them into mole. Remember that we said that molecules are moles of a compound, like the mole to mole ratio of how the compounds interact with each other. So if we are going to convert them into mole, we need to divide each by their respective atomic mass or atomic weight, which is measured in grams per mole. So that the gram would cancel gram, and then I'll just get mole left behind, right? So when I divide 40.9 by 12, 4.58 by 1, and then 54.2 by 16, the 16 being the molar weight for oxygen, 1 being the molar weight for hydrogen, and then the 12 being the molar weight for carbon, right? I get 3.4 moles of carbon is in the compound that we're talking about. 4.58 moles of hydrogen is in the compound that we're talking about, and 3.4 moles of oxygen is in a compound that we're talking about. Now you should ask, why is it that hydrogen had the lowest mass but it had the highest moles, right? The simple answer is that compounds combine in moles, the amount of substance in moles, not in the grams, right? So it doesn't matter whether it had the smallest grams. If its mole comparison makes it have the largest mole, so be it. So hydrogen will have the largest mole over here. And once we get them into the mole, we once stated that the empirical formula is the lowest mole ratio. It's the lowest mole ratio. So we have to find the lowest mole ratio. And for us to find the lowest mole ratio, we divide through by the lowest common multiple. So over here is was converting to moles. So over here is converting to moles. And then over here is finding the lowest mole number ratio. So here is finding lowest mole ratio. So once we did find the lowest mole ratio, we come down here and we had a fraction in it. If this did not have any fraction in it, it will be our empirical formula because it's in the lowest mole ratio. But we cannot have fractions lingering around on our thing, like how we solve the thing. So by so doing, we have to find a number that will multiply this fraction to equal a whole number. And in this case, it was 3. So we multiply each side by 3, each side by 3, each side by 3. And then the empirical formula that we alighted on was this C3H4O3. Please, is it understood? So if you want to find the molecular formula from this empirical formula, you can use the expression, the ratio of the molecular formula, over the empirical formula would directly give us the molecular weight that we do have here, 264 grams per mole, divided by the empirical weight that we're going to find here also. That is the empirical weight. So let's go ahead and find our empirical weight. So our empirical weight over here will give us this 3 that we have here. It's going to be 3 times the carbon, which is 12, plus the 4 times the hydrogen, which is 1, and then the 3 times the oxygen, which is 16, right? And 3 times the 12 is going to give us 36, plus 4, plus 3 times 16. So you're gonna get 48 over here. So if you sum these, this would give me 40. So I'll get 88. So I have 88 grams per mole. Grams per mole as the empirical weight, right? So if I want to find the ratio between its molecular weight and its empirical weight so that I could find the molecular formula, I just divide this 264 grams per mole divided by my 88 grams per mole, and then grams per mole cancel gram per mole. 88 goes here 1, goes here 3. I get my ratio to be 3. So once I have my ratio to be 3, I just leave this whole thing and multiply everything by 3. So I'll get here, my C would be C, 3 times 3 is 9. My H, 4, 3, 12. Like that. And then my O, 3 by 3 is also 9. Right? So this would be my empirical formula and molecular formula conversion, right? But there is a second method, a pretty simple one, but that also requires a little bit of nuance. Let me, so the first one, we did like a direct mass conversion. We did, we convert to moles, find the lowest mole ratio to alight us to the empirical formula. Now, if you want to know the whole number ratio that we will multiply by the empirical formula to get the molecular formula, we have to divide the molecular formula by the empirical weight. It's the molecular weight by the empirical weight. We have to divide the molecular weight by the empirical weight, and then by so doing, we find our whole number ratio. We multiply it with the empirical formula that we did find here, and then we get the molecular formula. So that is the first method we could go about it. Now the second method that we could also use in this approach, that it is one that I really like using, or when I encounter a question like this, that is my first instinct on how to solve it using common sense. So my first instinct was that let me turn all of this into decimals or fractions. So for the carbon specific, hydrogen specific, oxygen specific, right? So if I'm turning this into my decimals, it's going to be 0.49, right? So if I have 0.409, like this, right? And this 0.49 is me assuming that the entire thing is just 1 gram. If I assume that the entire mass of the sample is just 1 gram, this will just be 0.049 grams, right? Now, if I want to convert this into the moles, I have to divide by its respective molar mass, right? So 12 grams per mole, and this is 100 grams, 0.4 grams. Then I multiply all this, right, by the entire molecular weight of the 10 grams per mole. Again, this will give me the ratio of carbon inside the compound, right? Now I'll do the same for hydrogen. So it's going to be 0.0458 divided by 1, right? Grams per mole, multiplied by 264 grams per mole. Same thing for oxygen. It's going to be 0.542 grams divided by 16 grams per mole times 264 grams per mole. So in this type of venture, I am going to find the ratio of carbon in this thing to be. Now if I do the math, which looks complex, without a calculator, over here you're gonna get 9 moles, right? If you do the same thing for hydrogen, you're also going to get an equivalent of 13 moles. And if you do the same thing for oxygen, you're gonna get an equivalent of also 9 moles, right? But that is if we decide to do the math. If we decide to really do the math, so if you do this, it's going to be an equivalent of 9.3333 reoccurring. So we approximate it to 9 moles, right? Now we could go through the exact same thing and do it for this Mark II, but this shouldn't be that hard. So you will get a point. Divide by 16, you're gonna get this. So the general molecular formula. So this gives you straight away the molecular formula. So this was H. The straight away molecular formula that this is going to give you is going to be C9H13O9. But one thing that you should make in mind, or you should be aware, is that since we did approximation, and then also familiarity's sake, you're gonna know that this 13 here is wrong. It should be 12 over here. Why? That is why I said this method is kind of a nuance, because you end up with something like this, where this was 13. And if you do not take it, this might be on the answer choice on your gut, and you could pick it and get it wrong, right? So you can take your time and go through the first step and arrive at the concrete answer, or do this, right? Now, if we get here and we want to get into the lowest molecular, the whole number, the empirical formula, we divide here by 9, here by 9, here by 9, right? So 1, we're gonna get over here like 1.33, and then we're gonna get here 1, 1. So we multiply 2 by 4, 3 again, you get C3, H4O3, and that will be your empirical formula right then and there. Woo! So let's go on to the types of reaction. And this would be the types of reaction. After that we have time, we'll go through with balancing chemical equations. If not, we will just end here. So there are various ways in which molecules react with each other, right? Those are called the types of reactions. The first type of reaction that I want to look at is one, combination reaction. Now, combination reaction is pretty simple. It is just 2 or more atoms coming together to form one unit. So a combination reaction is 2 or more atoms. I'm not going to write 2 or more atoms anymore. I'm just going to write like you have A plus B. It gives you AB. So A combined with B to give you AB. That is combination reaction. Pretty simple forward, pretty straightforward. And then we have one thing too that we also call decomposition reaction, right? So decomposition reaction. A decomposition reaction is just the reverse of combination reaction. It's just one compound decomposing to form two or more products. So that one is going to be AB. Go there and form A plus B. That is a decomposition reaction for you. And then we also have combustion reaction, right? Combustion reaction. Combustion reaction. Now there are two things that I want you to put in mind in combustion reactions. In combustion reactions, one, there will be always oxygen, right, at the reactant side. So it's basically burning a fuel to produce heat and carbon dioxide, right? So a combustion reaction could be like CH4 plus oxygen would give you CO2 plus H2O. Now you can balance the chemical equation. That will be our next topic. We're not going to combine it. We're not going to balance it now. There is always oxygen here, right, in the reactant side, and you may form carbon dioxide and water. But one thing here is that sometimes the combustion is not complete. We call it incomplete combustion, and you form carbon monoxide, but you still form water though, right? So one thing you should put in mind to catch any combustion reaction is that oxygen is in the reactant side, water is in the product side. Carbon dioxide is not guaranteed. You can form carbon monoxide. You could form sulfur dioxide. You could be burning like a sulfuric substance, right? Like something that has sulfur in it, and you form sulfur dioxide and water. So carbon dioxide or carbon monoxide here, it's not guaranteed in a combustion reaction. So don't be like it always produces carbon dioxide. So put asterisk on it. CO2 is not a guarantee in combustion reaction, right? The second one, the next one that I want us to look at is single displacement reaction. Single displacement reaction. Now this is what I really want you to pay attention to. In a single displacement reaction such as this, copper, which is a solid, react with silver nitrate, right? Is it NO3? Yeah, NO3. To give you copper nitrate. Let me turn the camera over. To give you copper nitrate, right? What is the formula for? It's also CO. Copper nitrate plus the silver, right? Now, single displacement means the copper displaces silver, and then form a nitrate with it. Form a copper nitrate with it. There are some. It gets a little bit tricky over here because the question that you can ask yourself is that why did the silver let the copper displace it? Silver nitrate is a stable compound, all right? Why is the copper displacing it, right? That is where you come to the nuance of the reactivity series. Now, when you take the periodic table, let me draw a makeup version of the periodic table over here. This I'm more interested in the transition metals, right? Now when you take the periodic table like this, the transition metals, this is like a rule of thumb to go by when you are dealing with a displacement reaction to see which compound which metal will displace which other metal. When you draw a line at where iron and manganese is at on the periodic table, somewhere over here in the middle, right? All the atoms or all the elements that falls in the left side over here, they are more reactive. So all of these elements that are here are more reactive than those ones that are here. These are less reactive. So a rule of thumb, if you are having to do a single displacement reaction and you have a metal nitrate that falls, or any metal compound that falls within this side of the periodic table, and then reacting with one that falls on this side of the periodic table, this would displace this. The one that is more reactive would displace the one that is less reactive. So one thing that you should put in mind when it comes to single displacement reaction, reactivity wins, right? That is one thing. Another thing that you should put in mind is that when these compounds dissociate into their single ions in the aqueous solution, they try to make sure that the ending product has less ions in it, or would form some type of a precipitate, right? So as to conserve energy, or so as to be stable. So if you know your solubility rules, and then you could know that if a compound like copper joins with a nitrate, it wouldn't dissolve according to your solubility rules, then it will displace it and it will not be dissolved, right? So also solubility of compounds, Now the third thing that I want to also state over here, which is also a little bit of nuance, is that ideally when you take the transition metals, the industrial ones, right, the ones that are our day-to-day activities like iron, copper, cobalt, those ones that we do use it on our everyday day-to-day life, they are more reactive. So if you are dealing with a reaction like that and the metals that are in it, so let me put over here, one is everyday metals are more reactive, right? So they will win when you are dealing with it. Now there is no general rule as to why the copper will displace the silver. So these are some rule of thumb that I developed for myself when I was learning this thing, that if I do see something like that and on top of my head I do not know which is going to displace which, and it will come in handy in the next type of reaction that we will talk about, is that everyday metals are more reactive than the ones that we barely come across them. And finally, we have what we call noble metals. Right? The noble metals. Now, the noble metals are over here. Like on the periodic table, they form an inverted L. And there are just three of them. We have silver, which is Mr. Silver. We have gold, and we have platinum over here. So the noble metals, which is silver, gold, and then platinum, they are not reactive, right? So, or their reactivity is very low. That's why we call them noble metals, because they trying to mimic the noble gases over here. So once you get these things, the noble metals reactivities is down. Let's say you have a compound that a noble metal is fighting an everyday metal. Classic example, a noble metal is fighting an everyday metal. It won't win. Its reactivity is low. Classic. Right? Now I haven't got into solubility rules in chemistry, so on top of my head I do not know whether copper nitrate is insoluble, but I'm giving myself benefit of the doubt that copper nitrate might be insoluble. Also, the next reaction that I want us to go on to is the double displacement reaction, the DD reaction, not DD, it's DD reaction. The double, let me come over here and wipe this thing down. Let me clean this. And then let's go double displacement reaction. Double displacement reaction. Now, in double displacement reaction, you have two, it's like an exchange, right? We have two different elements or atoms on two different compounds switching positions. right? To form new compounds. And an example of that. And now in this reaction, where calcium chloride reacts with silver nitrate to produce calcium nitrate plus silver chloride, why would the calcium is double displacement? So the calcium displaced the silver, right? And then the silver took place of the calcium to form this, right? Now the reason why they did that, right, is due to some of the reason why I first aligned here. One is reactivity wins. Reactivity would always win. So, for instance, calcium, when you look at the periodic table, calcium is on what? Group 2, group 1. One of them is part of the alkali metal or the alkaline metal. It's highly reactive than this Mr. Noble silver over here. It will kick him out, right? And when silver ion is floating in the solution, since the end product, whereby if you write the net ionic equation, the end product want to limit the amount of ions in it, the silver can bond with the chlorine to eliminate that ionic thing in the solution. So the silver has no choice than to go bond with chlorine to become silver chloride. That is one reason why it will do that. So reason number one, still reactivity wins, right? Rule number 2 is also, these are rules that I developed for myself. Once again, I don't think you find them in any chemistry textbook. Rule number 2 is also that the ion charges, the ionic charges, would favor whichever would use the less energy in the bond. So ionic charges favors less energy, right, to bond. Now, in this point, what I mean is that, look over here. Calcium here on a regular day will be like calcium plus 2. They will lose 2 electrons. Chlorine atom on a regular day, so calcium over here will form a plus 2 charge. Chlorine atom on a regular day will form a minus 1 charge. So for every 1 calcium that you put in this solution, you need 2 chlorine to bond to it to form any type of neutrality, right? So if the ratio is 1:2, it is unfavorable. On the other hand, if you put Mr. Silver here in the solution, this silver will produce just +1, right? And when it produces the +1, it needs just 1 chlorine, right? So the ratio is 1:1. Small ratio, less energy, the bond will be favored. Bigger ratio, bigger energy, the bond will not be favored. That too. And then last but not the least, your solubility works, your solubility rules. So you really need to, when you get to solubility, you really need to get that down in order to do this type of reaction. The next one is your solubility. Now the main purpose, or one of the biggest purpose, or the biggest reason why this reaction would occur is because it wants to form a precipitate, so that the ions that are existing in the solution is minimal. So it will either form a precipitate, that is one. These are the ways whereby the solubility would work, or limiting the amount of ions in the solution. So let me even change this rule from solubility to limiting amount of ions, right? Amount of ions. So if it's limiting the amount of ions, you could do it in this way. One, solubility, right? Which one would form a precipitate? That is a precipitate. And the precipitate will not dissolve, so it will not dissociate into ions. The second one you could do this is to which one would form a gas, right? Which one would form a gas? Why gas? Because the gas would escape from the solution. And once it escapes from the solution, it is carrying with it whatever elements make up that gas, eliminating that ion specifically from the equation. So that is one way why this double substitution or double displacement reaction would occur. Now, last but not the least type of reaction is the neutralization reaction. The last one is the neutralization reaction. Now, neutralization reaction is an example of a double displacement reaction, whereby an acid will react with base to produce salt and water. So we take acid hydrogen chloride or hydrochloric acid messing around with sodium hydroxide, right? Sodium hydroxide to form sodium chloride plus water. Now, if you have just memorized a neutralization reaction, right, you just know that any neutralization reaction gives rise to a salt and water. But once you get complex into these type of things, then you are left to figure out why, because sometimes the reaction wouldn't go straightforward like this. So what will be your determinant for a neutralization reaction if it doesn't go straightforward like this? Like the salt that is formed is compound salts, like a very big salt, or the water that is forming some type of a hydrate water. Why? So the same thing, if you put up the rules that are put forward together over here, that I say that the ion with the highest reactivity would win. When it's sodium and hydrogen, when they come to reactant, hydrogen don't even come close to how reactive sodium is, right? Sodium is on the group 1 alkali F metal. It's so reactive such that even if it comes in contact with just water, it can cause fire. So it will kick off hydrogen and then bond with the chlorine, right? And then since the reaction, the entire thing wants to limit the amount of hydrogen in it, the amount of ions in it, it will have to kick out, or the hydrogen will have to bond with anything so that there is a limit of ion, and it will bond with this hydroxide ion that will be left in the equation, the solution to form water. And what is water again? Polar inert. It is not, it on itself doesn't have any ions. And what is this sodium chloride? This will be the only ion that will dissociate in the water, not hydrogen ion, chlorine ions, sodium ions, hydroxide ions. So in the next final equation, these ions and these ions wouldn't exist. It will just be this sodium and then the chlorine floating around in it, limiting the ions. So those are how this type of reaction goes. Now we would end here, and then on our next endeavor we will conquer balancing chemical equation, and then we will also go about finding limiting and excess agents, like reagents, and all those things. We will enter cations, anions, we will do ionic charges, and we will finally end it up with electrolytes. This is a heavy loaded chapter. Thank you once again. My name is Richard. It has never changed. And thank you for watching the video. God bless you.